All right, so we got this problem. Again, we're going to draw the shear force and bending moment diagram. Oh, I did leave off dimension. Let's make this 8 feet. Now, if we wanted to draw this, if we wanted to do this with equations, how many sets of equations do we have to write? Can we write? Well, let me ask you this: can we write one equation for shear force and bending moment that'd be valid for the whole structure? No. So I'd have to write one over this continuous load from, like, say, 0 to 12, and then a second one from 12 to 20. In fact, we might have done this something like this problem previously. And of course, once you have those functions, you could simply plot them. So just to kind of compare to what we did before, let's not do it that way. Let's try the shear force and bending moment diagram approximation that we talked about. So to begin, we need to find our shear force and bending moment over here at the reaction. So I'm going to go over here to the side and draw a free body diagram of the load. And on that free body diagram, at the fixed support A, I'm going to assume a positive shear force at A and a positive bending moment at A. Those are my two reactions. I'm going to convert the concentrated equivalent load here, the distributed load, to a concentrated equivalent load to make my work a little easier. And the value of that concentrated load is going to be the area under the curve, which is what? It's a rectangle, so this is going to be base times height. 12 feet times 4 kips per foot, so that's 48 kips. And it's going to act through the centroid of the area. Where's the centroid of a rectangle? Right in the middle. So that would be 6 feet from the end. And then out there on the end, I have an applied force of 60 kips and an applied moment, pretty big, 100 kip feet. The remainder of this distance here would be, since the total is 20, 12 plus 8, take away 6, this will be an additional 14 feet. So I'm going to look at this free body diagram here on the right, and I'm going to find my reactions. So I suggest that you start by summing the moments at A. That way the unknown shear force passes through A. It will not create any moment. So there's my equilibrium equation. So now let's apply it to this problem. So I'm using right-hand rule for my sign convention for my statics. So this moment is positive or negative? Negative. And both these two forces here are going to create what kind of moment about A? Positive or negative? Negative again. So the first one would be 48 kips is the force. And what's the distance? 6. And then the 60 kip force, the distance is, 20. And let's not forget this applied moment out here. So using right-hand rule as my sign convention, this moment is negative. So I can solve for my moment at A. It looks like it's going to be negative. Somebody's going to have to help me with this.
508.
Say again?
508.
508. Anybody else get 508? Exactly 508? Anybody else? Anybody playing along at home?
I didn't get it, but...
You didn't get it?
I did it wrong.
Try it again. I like to get, I don't remember this number. What'd you get?
1588.
1588.
That's fine. Negative 1588.
Mr. Lopez, try it again. 1588 somehow sounds familiar.
Yeah.
Okay, cool. So negative 1588, and that'll be kip feet. So what kind of moment do we have at A? Positive or negative bending moment? Remember, we assume positive, we got a negative sign, so it's negative bending moment. And then I can sum forces in the y direction, and make sure that's in equilibrium. And I'm going to assume up is positive, so this force is up, so it's positive. This force is down, negative. Out there on the end is also down, so that's negative. So it looks like my shear at A is equal to 108.
Yep.
And that's positive shear force. So now I know where I'm starting. I get all the way over here on the end. What should my shear force be when I get to the end of my beam? What kind of shear force does this create? Remember, my beam is going to come up just to the left of it. So on the left side, positive shear force would be up, right? So those are going to bounce, so I should end up with a positive 60 at the end. What kind of bending moment is this? Positive or negative? Negative. It has a value of 100. So my bending moment diagram should end at negative 100. So I know where I'm starting and I know where I'm going. Let's see if we can connect the dots. So I'm going to start by drawing a template. That's where I'm going to start. That's where I'm going to end. I got this point here that's a transition as I go from one load to another. That's probably going to be a point of interest, so I'll add that. And for now, that's enough to get started. So I'm going to go on to this template and assume my positive x direction, my positive value for shear, and all my units in shear will be in kips. So starting on the left-hand side here, what is my shear force? Well, that's A, and the shear at A is 108. Now remember, our relationships, the change in shear between any 2 points on the load curve is just the integral. So what's the change in shear from 0 to 12? Well, it should be the area under this load curve, which is what? It's a rectangle, so it's base times height. 12 times 4 is 48. Is that positive or negative load?
Negative.
Negative. So what's 108 minus 48?
60.
Comes out to be 60. And we also know that the slope of the shear diagram is equal to the load. Right? And what's the value of the load over the first 12 feet? It's constant and negative. So I have a constant negative slope. In fact, if I were to look at that slope, it would be, for every one I would go over, it would drop 4. So this first section looks like it's trapezoidal shaped. The change in shear from 12 to 20, according to this, it's the area of the load curve. And what is the area of the load curve? 0, so no change. So it ends at positive 60, which is great because we've already talked about it and we already knew that it should be a shear of positive 60. And the slope of the shear diagram is the load. And what's the value of the load? 0. So 0 slope. So that part is rectangular. And there's your shear diagram. This beam has positive shear everywhere. And where would be the maximum value? At the support. Okay. So let's now draw the moment diagram. So we'll assume positive x, positive value for moment. All of our values will be in kip feet. Now what's the moment at my starting point A? We saw for the moment A. There it is. It's negative 1588. Do we know what we should end at? Do we know the moment here at the free end? Yeah, it should be negative 100, which is not much, but I'll put it in there. So I know where I'm starting, and I know where I have to go. And the relationships that are going to help us connect those dots are that the change in moment is given by the area under the shear diagram. And then the shape of the moment, given by the slope, is equal to the shear. So let's start with the first one, the integral relationship. What's the change in moment between 0 and 12? Which should be the area under this shape of the moment diagram, right? That's a trapezoid. Now you can break it up to a rectangle or triangle if you want, but I just happen to know the area of a trapezoid you find by averaging the height of both sides. So that should come out to be 84 height. And 84 times 12 should give you the area. What's 84 times 12?
1008.
Huh?
1008.
1008. So that's positive. So negative 1588 plus 1008 leaves me what? 580? Negative 580, is that right? You guys doing this that way?
Yeah, you're right.
Is that it? So that should be negative 580. And what's the shape of the moment diagram? Well, it's given by the shear. And what's the shear? Well, the shear starts off at a positive value and decreases to a smaller positive value. So let's see if I can draw this in. So here's a positive value there, and this one is slightly larger. So you can see that my shape would be something like that. So this is first order linear. This should be second order quadratic. Now the change in moment between 12 and 20 should be the area of this part of the shear diagram, which is rectangular. So it should be 8 times 6, which I believe is 480. And that's also positive area. So 580 plus 480 does bring us to negative 100. Yay. And then the slope is given by the shear. And you look up here, the shear is constant all the way across, so you get a constant positive slope. So there's your moment diagram. Where's the maximum moment? As you might expect at the connection, has a value of 1588. Any questions about that one? I think that's test worthy. Not that this would be on the exam, but it's something like this I think is reasonable. Questions? All right, I'll stop it and we'll do some more.